gonna get started. So it's recording. As a precaution, again, I'm going to mute all. We had some experiences in the past with the sound, so the way we're going to do this, I'm going to mute all except the presenter, and this is the first experiment we're going to do. At the end, when we go to the FAQ, please, guys, use the chat room. I'm going to be reading the chat, and I'm going to be passing the questions to Brian. If you absolutely need to speak, then of course you can unmute your phone and speak. But just to avoid noise, let's do it this way, right? At the end in the FAQ, you use the chat. I read the question to Brian, and we move on. Okay. One more time. I'm going. Well, I think everybody's mute. As a matter of fact, Brian, we got 3 minutes past. Let's see. Let's wait a couple of more minutes, get more people to get in, and then you can go ahead and get started. Just 2 more minutes, please.
Okay, that sounds good.
Okay, let's get started, Brian.
Okay, that sounds good.
Just a brief introduction. Thank you for joining, Brian. Dr. Sloboda, he is the chair for the Quantitative Experimental Design, and we actually delighted that he's going to share it with us, his expertise. I do manage the non-experimental. I'm really eager to learn from you and use your knowledge and apply this to my students. So thank you for this presentation. The floor is yours. Go ahead, please.
Okay. Oh no, minor problem here. Okay, well, thank you very much, everyone, for coming today for the quantitative experimental design. So the last couple of weeks we've been having webinars on the different methods of qualitative research. So now we kind of go into a different direction. So again, welcome to the Quantitative Experimental webinar. And this is a continuation of our webinar series on research methodology to help you aid into doing your research. The next webinar is going to be next Thursday, how to use deduce for analyzing qualitative and mixed methods data webinar. So that's going to be probably a very interesting one as well. So what's going to be the overview of today? Well, basically I'll give an introduction to the quantitative experimental design and some of the standard methods that are used in the quantitative experimental design, such as one-way ANOVA, two-way ANOVA, and then MANOVA. And then there's going to be other approaches to randomized design that maybe that people may not be aware of, but they serve as the foundation for the study of quantitative experimental design. And then at the end, I'll have conclusion and closing thoughts on on what we covered today. So, introduction to the quantitative experimental design. When do we use this type of design? Well, the premise of quantitative research is we always have an independent variable and a dependent variable, or many independent variables and one dependent variable, but depending upon the type of design that you're looking at. And we're looking at relationships between variables. And quantitative research can be like very descriptive, like measured one time, or they could be experimental, such as they can be subject to before and an after treatment type thing. So I'll give you some examples of some before and after treatments throughout the webinar. And then a descriptive study just looks at what's the association between the variables. You know, you're looking at X and Y, what's the relationship? And that's basically what it is. An experimental design attempts to say what's the causality between the variable that was designed for the research. So it's a lot of stuff, and you know, when you're doing experimental design, a lot of things are basically, the objective is, okay, what's the causality? In other words, what causes what? And that's what we're going to be interested in, you know, what variable causes what? So what's the type of problem that's associated with this type of design? Well, this type of research is true experimental because this research establishes the cause and effect relationship among whatever variables that you have. So like I said, one of the big objectives is to sit and say, okay, we have this variable and causes that variable. We're trying to establish what's the causality, what causes what to occur. In a truly experimental design, we always want to identify and impose control over all the variables except for one. So an independent variable can be manipulated to determine the effects on the dependent variable. So you keep in mind, so independent variables are those type of variables that can be manipulated and onto the dependent variable. So I'm having a little bit of a static here.
Yeah, there is some noise that in the background. I'm trying to mute all, and I lost the ability. But there is some noise that I see if I can get rid of it. Waiting. Hold on, let me see if I can locate who actually is the one making noise.
Okay, so now we're going to be basically looking at the efficacy versus effectiveness. You know, when you're looking at efficacy, the benefit of an intervention compared to a control group or standard program under certain controlled or randomized situations. So remember, the randomized controlled trial is often designed that's going to be used when you're doing experimental design. But when you're looking at effectiveness, the benefit of the intervention under less controlled real-world conditions would be more of the quasi-experimental design, which it would be used. But I'm not going to cover anything on quasi-experimental design. That would be a separate topic for presentation. So for experimental design, the So the basic objective, we take subjects and we randomly assign to at least 2 comparison groups. The purpose is to compare 2 or more groups that are formed by some type of random assignment. And then basically the groups are solely differ based on what are the measurements. You know, what's the intervention that we're going to use? What's going to be something we're going to be looking at? And then for changes from pre-test to post-test can be reasonably attributed to some intervention. So for example, if you're looking at ASVABs that are often used in military, sometimes they give pre-test and sometimes they give post-test to see what type of intervention may have been used to determine what was the intervention and did it help. But the whole objective of quantitative experimental design is that it's completely randomized. It's the most randomized experiment that's out there. So when using the completely randomized design, the researcher is interested in the mean responses of the treatment group. So here's your experiment. Where's the responses? What do these responses tell us? So an example of this research design, an example of this research design is exposure to a new teaching method. So I kind of took this example out from educational psychology. So they often want to know, hey, we're using this new teaching method. Does it work or does not work? So during the teaching of this new method, researchers will attempt to control 2 groups that keep them identical and normal as possible. Then they're going to say, okay, let's have one group be exposed to the new teaching method. By doing the latter, this enables researchers to isolate the effects of this new teaching method. So the control group should almost be identical to the experimental group. And sometimes when you're doing these quantitative experimental design, one of the hardest parts is often going to be you have to identify what that control group is going to be. And in many cases, it's not very simple to actually identify it. And then when the experimental group is exposed to the change designated by the researcher, while the control group remains constant. You want to say, okay, we shocked or we experimented with one group and the control group stays the same, what were the impacts? So the first type of quantitative experimental design that everyone's probably aware of is the one-way ANOVA. So now I'll present some of the standard methods that are going to be used in quantitative experimental design. One-way ANOVA, two-way ANOVA, and MANOVA. And I don't intend to show any algebra, so you don't have to worry about any math. So it'll be all conceptual. But what is one-way ANOVA? Well, it's short for analysis of variance. And typically, for the most part, you have 3 or more groups to test for the mean differences. So even though it says analysis of variance, you're looking at all the changes that occur in the variances, but really the underlying change that's driving these changes is going to be in the mean. So for example, you have a caffeine study with 3 types of groups: no caffeine, mild dose, and then the jolt group. And then you can see what kinds of results that you get from that. In the ANOVA vocabulary, level is a value. It's the kind or the amount of the independent variable. The treatment group is those people in the ANOVA who are getting some very specific treatment or the level of IV, or independent variable. And keep in mind the treatment effect is the size of the differences in the mean. And then we always have to worry about what our dependent variable is going to be. So you experiment or you shock the independent variable, and then you want to see what's going to be the output or the effect on the dependent variable. So what's the rationale for the one-way ANOVA? Well, just you have three means to test. So we have the null hypothesis, mu1 equals mu2 equals mu3. Essentially, it's saying the null hypothesis is saying there's no differences between the mean, where everything is the same. While the alternative hypothesis just simply say at least one of the means differ. But remember, the test for ANOVA is going to say you could reject the null, and you should say, yes, there is one of the means do differ. It does not tell us specifically where those differences actually occur. Or you could take two at a time, but really want to test all three or more at one time. So the problem is, if you just do two at a time and do a t-test or a z-test, what's going to happen is it creates a higher type 1 error being committed. So instead of using the mean difference, we use the variance of all the group means about the grand mean over all groups, and then we test it. And then we eventually get an f-test to determine whether or not there's going to be any differences between the means. The logic is behind as the same as your t-test. Remember, t-test, you have two groups, and you might say, yes, there might be no difference between the two groups. So you compare the observed variance among the means, observed difference in the means in the t-test, and so we want to know what do we expect to get by chance. So one-way ANOVA is very straightforward task to do. Even Excel will do that. But let's continue on with the rationale with the ANOVA. Suppose we drew a sample from the same population. So you can see in the graph here what's going to be happening is the results may look something similar like this. So note that the means from the three groups are not exactly the same by looking at the behavior of the distribution, but they're very close to each other. So what's going to happen is, because the means are so close to each other, the variance among them will be very small. So you don't expect a lot of dispersion among these three groups. And it's quite possible that when you conduct the analysis of variance for it, what may happen is that you may wind up failing to reject the null and say they're almost all basically the same for these three groups. But let's say we have the same people from three different populations. So now our results may look something like this. Now we have something totally different. So we basically have a much greater dispersion than we did before among the means. So notice that the sample means are far away from each other, or they're much more spread out. So the variance among these means shall be larger. So given that you have these raw scores from these three groups that are much larger, what's going to happen is when you're doing the ANOVA, one-way ANOVA, what may wind up happening is you may have evidence that you could reject the null and conclude one of these means actually do differ. So another possible approach is suppose that we complete a study and we find the following results. So we have either graph. How do we know or decide where there's real effect or not? So that's where we compare our observed variance in the mean. So we look up the variances and if everything's attributed to the behavior in the mean. So what do we expect to get on the basis of chance, given there's no true difference in these means? So that's the whole rationale of what you're trying to show in the ANOVA. These are my groups and what is going on in each of these groups. So one of the good strategies that's suggested for doing an ANOVA, and sometimes people ignore, is to do the plots, see what's going on in terms of these plots like I did here, so you have a better sense of what may be going on in the data, and that will drive what could happen in your underlying hypothesis testing? Well, as I said, the mathematics for ANOVA is quite abundant, and it could be summarized by a nice little table. And the nice little feature about this table is no matter which software you use, SPSS, Excel, R, or any other package, it prints out this table and it fills it up with numbers. And you don't have to worry so much about what the detailed nitty-gritty of math to show the calculation. And I'm sure some of you are aware the actual calculation for ANOVA one way could be quite tedious, but the more groups that you have, it's probably going to be the more tedious that it's going to be. So it's quite probably very encouraged that you use SPSS, Excel, or R to do the calculation. So each type of ANOVA test is going to have its own table. So for this ANOVA test, you only have one F-test. So you only have one null and one alternative, and you test it to see if there's any of at least one of the means actually do differ. But once you, as I said earlier, one of for the ANOVA is going to say, hey, I rejected the null, and I know at least one of my means differ. But the F-test does not tell us distinctly where these differences actually occur. So that's where you have to use post hoc tests, or sometimes some authors might refer as multiple comparisons, same thing. If the F-test is significant from ANOVA, the researcher has a difference in the population mean, but you don't know where these differences are. It's just that, yes, you rejected the null. So remember, the alternative hypothesis says at least one of the means differ, but it doesn't tell us which one. So you can have three means, for example, A, B, C. So you can have A equals B is greater than C, or A is greater than B is greater than C, or A is greater than B equals C. We don't know. But those are the possible combinations that we have to think about. So we need to know where these means actually differ. There are multiple tests, but we're just focused on one for the sake of it, to make it simple. But I suggest strongly that if you're going to be doing an ANOVA, that you consult Judy Palin's book, Survival for SPSS. It's a really good book. And then Judy Palin lays everything out very nicely. And then she explains in plain English how everything is going to work. So, and she does a really good job on the post hoc tests too. So remember the multiple comparison, the post hoc procedures versus a priori comparison. So we only look at the post hoc. So the comparison, we always worry about the comparison wise error rate, which is rate minus alpha for each comparison. And then sometimes we worry about the experiment-wise error rate, which is the probability of making a type 1 error for all the set of possible comparisons. So that becomes critical. As I mentioned earlier, if you can do an ANOVA, but rather than an ANOVA, you can test two groups at a time. And let's say you have 4 t-tests, what's going to wind up happening is the type 1 error is going to go way up. So it's just better to do an ANOVA because it's going to be quicker, easier, and more efficient to do, and then you'll make a less type 1 error. So how does it work? So recall from an earlier slide that there's A, B, and C. Then the researcher needs to do 3 total comparisons, A, B, A, C, B, C. I saw a question pop in by Ryan, and yeah, you're kind of right about that. It flashed on, it flashed off real quickly. But so the experimental design without any adjustments would be alpha equals 1 minus alpha all the way down, and then you can be able to calculate what the experiment-wide errors shall be. And then a common method that's used is going to be the Tukey HSD, which is maybe used with equal sample size per cell. And HSD means honestly significant difference. And then how do you actually calculate it? The formula is here. Q alpha is the value from the table of the studentized range statistics based on alpha. And then MSW is the mean square with groups from the ANOVA table. And then N is the number of people in each group. And then in this test, or there are two key tests, you have to make sure that each sample or each group is going to be the same size. Well, as I showed you here, there's a little formula here, a power test statistic to do the calculation. Hey, but guess what? SPSS will be able to do all the work for you. So when you're going to SPSS and you do the test for ANOVA, you just make sure you select which type of post hoc test that you might be interested in. And most people tend to maybe pick Tukey and then maybe like the Bonferroni, I think what Ryan just mentioned. But those two appear to be probably the most commonly used tests for post hoc. Unfortunately, Excel does not do this. So in Excel, you have to kind of create your own formulas and do it the longhand way, and then plug in numbers and see how it works. But the more groups that you have, the more complicated it is to develop all that. So that's what you want to keep in mind. But SPSS is really, really superb when it comes to the Bonferroni or Tukey or any other types of tests. So let's conceptualize the one-way ANOVA. I kind of gave like some conceptual information, but how can a researcher actually be able to know they can use a one-way ANOVA? Well, this is actually from a course assignment that I had some time ago. And the research, so the basic objective is, does the independent variable, i.e. belongs to a group, religion, social class, and race, explain the variation of the differences in the dependent variable of IQ? So you remember when you're doing research, one of the things you have to know is, okay, the first part is, this is from a course assignment, does the independent variable belonging to a group, religion, social class, race, explain variation, differences in the dependent variable of IQ? That's your general idea, but maybe sort of related to perhaps to the problem statement. But then you have to say, okay, your research question needs to be aligned with the problem statement of sorts. So you have to phrase the question in a way that exhibits an ANOVA. Does the average IQ differ among the working, middle, and lower class individuals? Because here we're asking a question, yes or no, and then of course you'll have to do some post hoc tests if it's the case, if you reject, and then you have to be able to explain those results and what does it mean. So what are we hypothesizing? So the average IQ for each one social class is going to be different from one or more of other social classes. And again, you have to make sure the research questions align with the ANOVA. You just can't say, I want to look up the difference between group and the differences in IQ, but what groups are you basically focusing on? So you got to make sure that the research question is aligned to the problem statement and the research purpose and so on. Now, the thing about it is everyone thinks one-way ANOVA is pretty straightforward to do, but what about a two-way ANOVA? You can have as many ANOVAs as you want, really. But ANOVA one-way only has one dependent variable and one independent variable, a factor. And recall that I was looking at does the independent variable belonging to some group explain variation in the dependent variable? What if you want to use two or more independent variables? You want to compare belonging to a group and by gender. This is just an example. So if in this case, you're going to have two independent variables, gender and group. But the process, and you want to know, is that going to have any impact upon the IQ? So the process is going to be the same as basically as a regular ANOVA. But the only difference now is that the calculation by hand becomes more tedious because instead of one independent variable, you're going to have two. So when we have two independent variables, we just say, hey, we have a two-way ANOVA. So in a two-way ANOVA, we investigate everything simultaneously. We investigate them simultaneously. And then the two-way ANOVA is basically going to say, hey, what's the effects of either factor alone? In other words, you belong into a group and by gender, and what are the impacts not impact, but what are the factors together if you looked at it both a group and by gender? So to look at both factors together is the advantage of a two-way ANOVA compared to a one-way ANOVA. And I always like to say that in a one-way ANOVA, you might have a bit more variation than you would in a two-way ANOVA. And then with the two-way ANOVA, what's going to happen is you're reducing that variation. And so actually, you can, by doing this isolation, you can see what the true effects might be. But the two-way ANOVA, the effect of the population mean of the dependent variable will often be attributed to whatever the levels of your factors are, and that's going to be your main effect. So this is what the researcher would detect when you're doing two one-way ANOVA. So yes, rather than doing a two-way ANOVA, yes, you can simply just do one ANOVA, and then you can do a second one-way ANOVA. You can do it that way too. But it may not be, but in terms of actually being effective, it may not be showing you what the interaction might be. So what could be the hypotheses for the two-way ANOVA? Well, there's two questions that are going to be answered by a two-way ANOVA. Is there any effect of factor A on the outcome, the main effect? Is there effect of factor B on the outcome? So in a one-way ANOVA, we only have one hypothesis. Typically, in a two-way ANOVA, you will have two hypotheses. But if you throw in the interaction effect in the two-way ANOVA, you're not going to just have two, but you're going to wind up with three tests for ANOVA. And then you have, because you'll be looking at the interaction between the two effects, A and B. So like the hypotheses, like I've shown on the previous slide, the main effect of factor A, so we can say that all of the factors are going to be equal to 0, and then we'll say the alternative hypothesis, not all are going to be 0, or at least one is not going to be 0. Then for the second one, the main effect of factor B, which will be denoted by beta, which will be beta 1 equals beta 2 equals beta 3 equals 0. That means there's no differences. But then the alternative is going to say, hey, probably if at least one of them are going to be different. So the nice, as I mentioned earlier, the nice feature about SPSS or Excel, what's going to happen is if you do two-way ANOVA, it's going to produce a two-way ANOVA table, and you can see the output from the testing. So what's the hypotheses in plain English? So the effect of belonging to group factor A and gender factor B on the IQ, that's basically the premise that you'll be working from. So the null hypothesis for the main factor is there's no differences in the IQ across different groups. And that's if you belong to a group. then the alternative is going to say, yes, there is a difference. Then for the second factors, which is going to be based on gender, and then the null is there's no difference in IQ based on gender, but the alternative is going to say, yes, there is a difference. There is a difference in IQ based on gender. So we can conceptualize it. So this is sort of from a class assignment that I saw some time ago. There's two independent variables, political party and gender, with a dependent variable of attitude about a tax cut. Well, so, and the research question that aligns with this is there an interaction between the gender and political party affiliations regarding opinions about the recent tax cut? So people's attitude of a recent tax cut would be the dependent variable, and the genders and the political party affiliation would be more of the independent variables. So we're hypothesizing gender is one variable that looks at tax cuts, and the other variables is political party affiliation. So some would argue, well, maybe could extend the analysis, and the student did for their master's paper, and they will argue that educational status could be another independent variable. So that means you have a bigger ANOVA to assess. And I remember I was telling the student, you know, maybe it's not so much, I mean, I was sometimes, I maybe think gender may not be a big, the results of it, as I recall, was that gender didn't really have a strong effect on the opinions of the tax cut at the time, not the current tax cut. This was an earlier one. And then you may have to look at educational status. That might be a bit more, that might tell you a different type of story as opposed to gender. Gender did not reveal any importance of people's attitudes towards a tax cut, which was kind of interesting, but that's in two-way ANOVA. So I didn't show the big complicated table for the two-way ANOVA, but feel free to find some data for two-way ANOVA and run it in SPSS, and then you can see the nice old two-way table. And yes, you can test also the post hoc as well in two-way ANOVA. So no matter what version of ANOVA that you have, you should always consider doing post hoc tests. That way you want to know where these two different changes are occurring, or the true differences in the means. But there's another type of ANOVA, which is quantitative experimental design, is the multivariate analysis of variance, or MANOVA. It's just basically an extension of an ANOVA in which you look at the effects and interactions by the combinations of the dependent variable. Remember, in ANOVA, you just had one dependent variable. MANOVA is going to be more than one dependent variable. So what you're going to do is you're going to test the differences among groups on a combination of the dependent variable is likely to occur by chance. So essentially what you're doing is you're taking some type of linear combination of all these different variables, and you want to know, is there anything that's going to be significant that's going to be shown. I presented a little bit about MANOVA on my SIG piece, which I have listed here, but I didn't go too much into it. But it's used quite frequently in some business and psychological applications. So, but it is out there. But the mathematics underlying MANOVA is even worse than the ANOVA. So MANOVA, a little bit of technical note here. A new dependent variable is created that's a linear combination of the independent dependent variable, and you want to do that because you want to look at the differences between the groups. And there's another type of approach known as factorial design of different linear combination of these dependent variables, and you want to look at what are the main effects and what are the interactions that are actually occur that could affect these different groups. Also, when the independent variables have more than one level, what's going to wind up happening is you can take all your dependent variables and recombine them to maximize pairwise combination. So this is kind of like a little technical note on what's going on with ANOVA. I was going to show the math of this, but I figure I will pass on that for now. And then the thing about MANOVA is it can get quite complicated, and then once it gets complicated, then your actual estimation, and then you get your estimates, and then it becomes a big mumbo jumbo, and you got to kind of figure out what's going on. So I have a little picture here. Under most circumstances, the more complex the analysis is, that means in a MANOVA, what's going to wind up happening is going to reduce the power of the test. So that becomes a thing with MANOVA. So MANOVA is that the more complex the design, probably the more difficult in interpretation, but the reduction in power of the test. By measuring multiple dependent variables, you increase your chances of being able to find some difference. So with a single dependent variable, you're basically putting all of your eggs in one basket and saying, okay, this is going to be my outcome. But with a MANOVA, you have different multiple dependent variables, and you can see where the differences might be. So multiple measures generally do not cost a great deal more, but perhaps in a MANOVA, you're probably likely to find at least one difference, perhaps. So the main advantage of MANOVA over ANOVA is that when you're using multiple ANOVAs instead of doing a MANOVA, the type 1 error goes up. And under rare circumstances, under MANOVA, you may find differences, but these differences may not even show up in ANOVA. So there could be, when you're doing a MANOVA, remember you're creating linear combinations of your variables, or dependent variable, and you're trying to identify perhaps where these differences are. But under ANOVA, you don't have that. You only just have one dependent variable and perhaps maybe one or two independent variables, and you can't decipher that. So that may be a big difference as well. And then which dependent variables are going to be most important? This is a common question to ask when doing a MANOVA. Everyone wants to know, I have 4 dependent variables, which one is important? If there's any significant main effects or interaction in which the dependent variable is the most changed, if any, it may be caused by the different levels of the independent variable. So it's not so much what the dependent variable is happening, it's what's the composition of your independent variable that may be driving this. And then once you have a significant MANOVA, you can do single ANOVAs just to see what type of effects that you might have. So you can do that too. And then also sometimes you might be interested in knowing which levels of the independent variables are significantly different. Well, if there's significant main effects on the independent variables, then you have more than 2 levels, you're going to need to test which levels are different from each other. It gets complicated. And if there's interaction, that makes it even more complicated. You need to be taken apart so that the specific causes of these interactions can be uncovered. Again, this makes MANOVA a bit more complicated. And to be quite honest with you, the more complicated the MANOVA is going to be, it's probably going to be more difficult to get that high level of power and perhaps any other matters as well. And as I mentioned before, the Judy Palin's book, the SPSS Survival Manual, she does a wonderful job kind of outlining the complexities of MANOVA in written in plain English, and then she does a fantastic job trying to do that. And then with the proportion of the composite dependent variables explained by each independent variable. So you have to think about with the strength of the association between all your independent variables and each dependent variable separately. So if that's what you're kind of interested in knowing about with the results from MANOVA, you better consult Judy Palin's book. She kind of outlines this a little bit too, and kind of explain how you can do this in SPSS, so you can identify these things. So now we'll be conceptualizing the MANOVA. This was actually from an actual dissertation that I was involved with some years ago. And the gist of the study was to investigate the mean group differences on the scores of the OSIR. It's a survey instrument for experienced professionals. And the independent variables were basically age and gender. And then the three dependent variables, there's three, because would be occupational stress, psychological strain, and coping resources. So what was the research question that aligns with the MANOVA study? Well, do the group mean differences between the three EA professional age group and burnout on the measures for occupational stress, psychological strain, and coping resources? So that's what she had to do in her study. And before, originally she did it as a regular ANOVA and just did all these different ANOVAs, but then we were like, why are you doing this? And then we told her it's probably best to do a MANOVA. So other approaches to research design, and this is the topics that I mentioned here, all these papers and stuff, they're very, very common, but a lot of people don't really know about this when they're doing quantitative experimental. These papers by Rubin looks at all this information concerning the causal effects. That's what people are interested in. You know, when you're looking at potential outcome, paradigm differences, and so on, what's causing what? So put in another way, these models are looking at possible outcomes rather than the goal of a single outcome. And then the most common part is the Rubin causal model, was coined by Holland in 1986. So if you're interested in these other randomized design, that paper by Holland is probably the one you should kind of read to kind of get the back contextual information of the whole entire thing. And then the RCM, the Rubin causal model, basically is the foundation for quantitative experiment in both statistics and econometric analysis. So it lays the foundation. As a matter of fact, the RCM is also showing up in the machine learning literature, because machine learning, it basically focuses on predictive behavior, but now there's some research that's being conducted looking at the causal implication, what variable causes what, and then the foundation for it is going to be the RCM. So Rubin emphasizes looking at the relationship between the assignment and the treatment and outcome. Well, the simplest form of an assignment is randomized, to put people into groups. So it's independent of the covariates as well as the outcome. But remember, RCM uses potential outcome. However, one of these can actually be observed and the other one may not be, and you'd be assigned for treatment. So the whole second bullet point is what Holland in 1986 refers to as the fundamental problem of causal inference. So what does that mean? In plain English, individuals who we observe under treatment, we may have to form an estimate of what they would look like if they had not received the treatment. So that lays the foundation for the causal inference. What causes what? In a good but analytical paper, Imbings and Wooldridge, they discuss further the advantages in thinking terms of potential outcomes. So in economics and other social sciences, there's much interest in looking at things in that way. So then RCM is a foundational for causal analysis, especially if you're doing a valuation study, and then you want to use the DID estimator, or known as the difference in difference estimator. That all falls under here. So it forces you to think about what causes what. The questions of effect of fixed individual characteristics like gender or race, well, you don't care about those because those are fixed. So you can't worry about those variables. And then the most second important part of RCM is the estimation of the treatment effects and whether or not there's going to be uncertainty. And Holland and even Rubin suggest that uncertainty is not about sampling variation. So uncertainty does not revolve around that. So the entire population of observed outcome would not redress the fact that, hey, you may only have one outcome that's observed for each individual unit, so the counterfactual outcome must still be estimated, but you don't know it very well, so you have to have some uncertainty in that case. And then RCM still continues to be advanced. There hasn't been any lots of advances in that area. Use of instrumental variable methods, panel regression, regression continuity design, quantile regressions, and other empirical approaches. And a good book that covers that is Anglist and Pischke. And it's a very good book called Mostly Harmless Econometrics, and they go through all this very nicely. It could be a little difficult in some places. And then there's another book by Anglist and Pischke that came out a few years ago called Mastering Metrics. It's a little bit more plain English version, and it kind of goes through these different methods, instrumental variable, panel regressions, and so on. But the RCM is a very dominant framework, and the more recent literature has been stressing functional forms and distributional requirements, which I didn't really cover much, and the changes in functional forms, as well as you can allow for different types of heterogeneity and so on. So FPSS does not handle these recent advances very well, so you have to use another software called Stata, and you can actually buy a student version of it, or you can get a regular version of it through Stata and request it from using an affiliation with University of Phoenix for like $300, so $300 to $400, and it's a perpetual license. So it's a pretty nice software to learn. And thank you. And if there's any questions, just feel free to let me know.
Yeah, we do have some questions, Brian. And first, I need to apologize. At one time, I lost being the host for some reason, and I couldn't mute the phones, no matter how I tried. So finally, I was able to claim the meeting. I had to enter a password, and I became the host, and that's what I was able to host everybody. So it was a little period of time when we had a lot of noise.
Oh, right.
And I think I know what happened, but we can discuss that on the organizers. So we have two questions to begin with that were posted on the chat, and feel free to post more questions. I'm going to be grabbing them one by one, but the first question is, what non-parametric equivalences exist for ANOVA, MANOVA?
Now, can you repeat the question again?
Yes. What are the non-parametric tests that you can run instead of ANOVA or MANOVA that are parametric tests? What are the equivalent non-parametric tests that compared to ANOVA, MANOVA?
I think I'm assuming that if you're looking at ranked data, which I'll probably assume that, and it's non-parametric, probably the And I'm assuming that based on the question that you still want to do some type of an ANOVA analysis. So if you're going to do some ANOVA analysis, you can use the Kruskal-Wallis test by ranks, or the Kruskal-Wallis H test. The Kruskal is spelled Kruskal-Wallis H test. I hope I spelled it right, but that's what it sounds like. That's the approach that you can take if you have rank data. That's what I'm assuming that's being asked.
I guess, yeah, I think that's what it is. If the question was answered, we move on to the next one. Otherwise, you can always chat more, and I will post it back to Dr. Sloboda. Next question is, would you recommend MANOVA if we found issues with normality and a small sample size? I would maybe add a little bit that if we find issues with the ANOVA assumption, so would you recommend MANOVA?
One of the key things is when you're doing a MANOVA, and what you need to do is you need to test some assumptions to make sure that you actually meet those assumptions before you can actually run the MANOVA, making sure there's the issues of, it's not normality, it's going to be multi-normality and the covariance, multivariate covariance matrices and all these things. So you need to do that before you actually run the MANOVA, or your results will look a little, or results may not be quite interpretable.
Thank you. Any more questions? As you learn, we are recording this. It is going to be available in the Research Hub. And the way we do this, we put it as a stream as opposed to download that takes forever. You can always come back, click the link, and you're going to be able to listen to the whole presentation as many times as you want. Any more questions? Well, I guess no more questions. Okay, I think there is one question here. Yes, this is from Ryan. Are there special considerations for single subject research designs as opposed to between subject designs? I don't know if Brian, you can always get the microphone and speak it up, but I think I captured what you were saying.
So when you're saying special, so the question kind of deals with, are there any special considerations for single subject research designs? And my question is, what do you mean by special considerations? That's my thing.
Ryan? He says that may not allow parametric tests.
Oh, so I'm assuming that you basically may have like rank design, rank data.
He says yes, or they are not independent samples.
Oh, so if they're not going to be independent samples, then if you do this, you have to be very, very careful. But there are other ways around it that you can deal with those if their samples are not going to be independent. I probably would go that route instead.
Could it be, Dr. Sloboda, we're talking about reputed measures when we actually measure the same group?
Based on what Ryan is saying on the question and some of my follow-up, that's what it sounds like.
Yeah.
So it might be some type of repeated measures or something like that because you're using the same sample or more than once. in different circumstances. So that's what it sounds like. So I'm hoping I'm interpreting what Ryan is saying correctly.
Yeah, that's what he said. Right.
Yeah.
Indeed. That was a
Okay.
measure.
That sounds good.
Actually, Dr. Sloboda, I believe MANOVA handled that pretty well because the same subjects are repeated many times, and the ANOVA repeated measure take care of, I would say, take care of the noise, right? Because we are measuring the same guys.
Right, that's correct.
Very well.
And then I had this question. I don't remember where the question came from, but I can't remember who it was, but the researcher had ranked data, and it was non-parametric, and there is no non-parametric version technically for MANOVA. So in theory, you could technically use a regular old MANOVA and be able to use ranked data to actually test it. So there's no hindrance about that you have to all do that. There is no non-parametric version of MANOVA. So if you have that kind of data and you have a MANOVA, you may have to just use a regular one.
Thank you. The question from Paula Miller is, would a literature review study be possible for this type of design?
I think so. I think the problem is that it would be quite exhaustive because you have the different types of ANOVA and then MANOVA and then the recent advances that I was talking about earlier with the RCM models and the content of instrumental variable, panel regressions, and so on. So the literature review on something like this would be quite lengthy. It might be good for like a handbook in statistics, but I have not seen one on that. But yeah, it'd be quite exhaustive, yeah.
Thank you. Any more questions? Okay. Just a question from Mansoura, and I want to echo that. That was a very extensive, very detailed and informative presentation. And you know, the beauty is that we can always go back to the video, right?
Right. That's true.
As many times as we want, and we can maybe even make it available for the students. So that's beauty, right? That's beauty. And thank you, because that's what we're trying to do, elevate the rigor at these Phoenix dissertations and get our students to the next level. So with that said, I'm going to stop the recording, and thank you. I will be posting the minutes, the links, and in the research hub momentarily. Thank you very much.
Okay. Thank you very much, everyone.